Hello everyone and welcome to this lecture. In the last lecture, we have seen a brief introduction about sensitivity conjecture. Okay, it tells that sensitivity is polynomially related to block sensitivity of a Boolean function, and towards the end of the lecture we have seen that Lineal and Gaussman has given a graph theoretical version of this conjecture. Okay, and today we will prove this beautiful conjecture in very elegant way. This elegant way was given in very recently in 2019 by How Huang. Okay, it requires a very we have already learned the gadget we need to prove this beautiful theorem. Okay, very good. So let me first write the graph theoretical version of sensitivity conjecture, and then we will be heading towards the proof of it. Okay, yeah, so the graph theoretical version of sensitivity conjecture. Yeah, sensitivity conjecture. Great. Now it's a theorem, so let me write actually as a theorem also. Theorem 2019 by How Huang. Okay, sorry. Very good. Great. So let me first write the statement. Okay. So statement: let H be an induced subgraph, vertex induced subgraph of hypercube Qn. Okay, so it will have 2 raised to power n vertices with the number of vertices in n. So number of vertices in H is 2 raised to the power n minus 1 plus 1, basically 1 more than the half of the number of vertices in Qn. Then what? The maximum degree of H is at least square root of n. Okay, so we will prove that. And also in the towards the end of the last lecture we have seen that I told you that the adjacency matrix of Q1 may not help. The eigenvalues of the adjacency matrix of Q1 may not, even though we have calculated, I have written the expression of the eigenvalues of Q1, but it might not help. We need some different matrix which is kind of looking like adjacency matrix of Q1 but not exactly the adjacency matrix. Okay, because we already know the relation between the eigenvalues and the largest degree of graph. Okay, and then okay, so let us try to cook a new matrix, okay, which will be kind of similar to adjacency matrix of Q1 but not exactly. That's okay. So that matrix. Okay, so let us start with that matrix. Okay, so the matrix let us define, and that was very cleverly defined by How Huang. Okay, so let us consider the following sequence of symmetric matrices. Okay, so where the first term is basically the first matrix is nothing but this, and for any an, okay, this is an minus 1, then identity matrix minus an minus 1. Okay, then the claim is very nice claim is then a square n A square n is nothing but n times the identity matrix, which essentially means that, which will tell that later that and the eigenvalues of an are square root of n minus square root of n, each with multiplicity. How much? Each with multiplicity 2 raised to power n minus 1, half of, basically. So remember, what is size of an? Size of an is nothing but 2 to the power n times 2 to the power n, right? Okay, because each times we are doubling it. Very good. So great. So what about the proof of it? What about the proof? Proof is Very simple. Okay, as I already told you, this proof is very elegant, very simple to understand. Okay, so let us prove that in a square n is nothing but n times identity matrix. Okay, why is it so? Immediately, I mean, we can guess that we can prove it using the induction. So when n equal to 1, this you just see that when for n equal to 1, there is nothing actually to prove. Just multiply 0 1 1 0 with yes, again the same matrix. It will indeed give you identity matrix. Okay, so it will give you, yes, identity matrix. Very good. So n equal to 1, it is giving you the, very good. Okay, now let us assume that it is true for any n minus 1 matrix. So in the hypothesis, okay, by hypothesis, let me assume that a square n minus 1 is nothing but n minus 1 identity matrix. Okay, very good. Okay, now it is actually pretty much easy. So what will be a square n look like? A square n is nothing but, so let me write down the same structure again. So this is a n minus 1 identity minus a n minus this. Okay, and then you multiply again. Okay, identity minus a n minus 1. Okay, very good. Great. So so let me simplify it. So this will be, a square n minus 1 and then plus identity matrix. Okay, plus identity matrix. The second thing is I think this will be 0, big 0. This will be again a big 0, and this will be what? So this line, so I plus this, right? A square n minus 1. Very good. Okay, now just use the induction hypothesis. This is nothing but n minus 1. This is n minus 1 times identity matrix plus identity matrix 0 0 I plus n minus 1 times identity matrix, and this proves that the square n is nothing but n times identity. Well, basically this is n into identity matrix. Very good. So remember that I had this size 2 raised to power n. Okay, very good. So what next? Now we have to prove that the eigenvalues of a and r is square root of n and minus square root of n. Okay, this is actually just coming from this matrix itself, because a square n is equal to this. This implies that n square root of n and minus are the eigenvalues of an. Okay, but what about the multiplicity? Okay, remember that the trace of a is what? Trace of a, if you see, trace of a is 0. Okay, trace of a is 0, as the trace of an is 0. This implies that each of these eigenvalues will be with same multiplicity. That means half a multiplicity will be dedicated to a square root of n, half will be minus of square root of n. Okay, so eigenvalues are, this implies that the eigenvalues of a and r okay, is square root of n comma square root of, let me write just in dot form. Okay, dot is square root of n with multiplicity 2 raised to power n minus 1. Okay, and rest eigenvalues will be again with dot minus square root of n 2 raised to power n minus 1. Okay, now before moving ahead, if you see it carefully, the shape of this matrix an, okay, it is actually what? It is like I would say the signed version of adjacency matrix of hypercube. Okay, so basically if you see so let me again write. Okay, it's kind of signed version of the adjacency matrix of Qn, ANH. Okay, remember AN was what? Okay, so we were defining it like this: AN minus 1 I and then minus AN minus, right, where A1 was nothing but this, right, 0 1 1 0. Okay, now if you see, I mean, if you write the structure of adjacency matrix of any Qn, okay, so remember in the last lecture we have seen that, so these can be adjacency matrix, basically a hypercube can be seen as actually, so there are two hypercubes of size n minus 1, basically the number of vertices here will be 2 to n minus 1, okay, so n minus 1, and then corresponding vertices are connected by nh. By basically matchings. Okay, now it is not, I mean, if you see, let us see what A1 will be. So Q1 is what? You are this graph, right? Okay, and the adjacency matrix is basically here the adjacency matrix coincide with this AN, right? Simply. Okay, now what will be the adjacency matrix of Q2? Q2 will be like this, right? So what will be this? So in fact what we can do is we can actually copy AN 2 times here, right? You copy AN here 2 times, AN and then AN, okay, and these edges which are matching actually, so these are edges, so you just put identity matrix right here, identity I 2 cross 2 matrix, right? But this is basically here will be the adjacency matrix, but if we want to make the signed version of this, right, we just make minus. Okay, otherwise just like the adjacency matrix, in this way you can do for any Qn. Okay, very good. So yeah, okay, in fact if I write it more clearly here, so here what will be the basically the sign of the edges here it is positive, so here I can actually write it, so so this edge you can actually mark it as negative, okay, this one corresponding to this A2, right? Similarly, if what you do for Q3, okay, Q3 in fact you can do the same copies of this, so let me write the same copies. So one copy is this, okay, and you again write with this negative sign, okay, and another copy maybe again, so maybe this, let me write again the same copy, so 0 0 0 0 again, okay, but by the way now you see that for the again if I have to write the A3 here, okay, I have to put minus of this part, right, minus of this part, right, minus of A2, so that means whatever was the positive edges I will replace it by negative edges, or whatever negative we will replace by positive, so these edges will be this, right. Now this will be plus, okay, now remaining off diagonals are just matching, so you can just match by this, so this will be matched to this, this will be matched to this, this will be matched to this, this will be matched, this is Q3 and A3 is this, right, and if you add if you replace negative by plus, this will become the adjacency matrix of Q3. Very good. Okay, now the next result is, we need just the next result, and the proof is in front of us. Okay, very good. Next result is this, okay, theorem, let G be a graph, okay, and let AS be the signed adjacency matrix, be the signed adjacency matrix of G defined as follows, okay, so this says that Aij, and this is symmetric matrix, it is a signed adjacency matrix defined as let be the symmetric signed adjacency matrix of this, so basically this will be either 1 or minus 1, okay, if there is an edge between I and j, otherwise 0. Okay, so basically it's adjacency matrix wherever some basically for any edge ij, if there is 1 you can replace it by -1, and of course you have to make it symmetric, so ji entry will be same as ij, okay, and okay, if ij otherwise 0, okay, then we have seen one result, and this result holds for this matrix also. The maximum degree of G is always greater or equal to the largest eigenvalue of signed adjacency matrix. Okay, in fact if you replace sign the minus with plus, this is adjacency matrix, right, and this holds. So we have already seen that. Okay, so let us prove this by, I mean in the case of sign, right, so the proof is almost the same. Okay, proof is almost the proof. Okay, suppose let you assume that V is eigenvector corresponding to the largest eigenvalue of AS. So AS V is equal to, suppose, lambda 1 of the largest eigenvalue. Okay, so lambda 1 V. So lambda 1 is nothing but the lambda 1 of the AS. Okay, so largest eigenvalue of it. Very good. Very good. And assume that like earlier technique. Okay, so assume that suppose V1 be the largest modulus entry, the largest largest entry, okay, largest entry of V with respect to modulus, with respect to absolute value, okay, absolute value, let me write value here, okay, with respect to absolute value, then what you see that due to this definition, okay, so lambda 1 V1, okay, the largest entry is nothing but this, right, this basically the first entry of this, right, the first entry of this. Very good. And this in fact by the adjacency matrix, signed adjacency matrix definition, we can in fact this write as this is equal to summation over all the neighbors of 1, right, so suppose I is neighbor of j, so no this is 1 is neighbor of j, okay, and then this is nothing but a1j, okay, the first a1j, and then vj, okay, vj, the vj is jth entry of vector v, okay, very good. Yeah, so this is now, okay, now next thing is what, this you can always write as this, right, so you can take the mod inside, aij, sorry, a1j rather, I'm making mistake here, aj, okay, and then what, 2 times, okay, so this is actually less or equal to, yeah, very good, great. What next? This further I can write as this, right, absolute value of these numbers, and then yeah, so this is again 1 neighbor of j, okay, then mod 1j, then what, mod vj, very good, okay. Now there will be few more inequalities, and let me keep on going. Now vj is this quantity is always less or equal to v1, because v1 is having the largest modulus, so this quantity can be actually written as this, right, so 1 neighbor of j mod 1j, okay, and then v1, okay, very good. And the last thing is what, remember this tells what, this overall, if you see that this actually you can write, because v1 is constant, you can take outside, okay, and then this whole quantity, if you see that this is nothing but sum of the entries of the first row, which will be always less or equal to the maximum degree, okay. So let me first write it as that v1 summation 1 this 1j, okay, and then this is now clear, which further less or equal to mod v1 okay, and this is nothing but basically this quantity always less than maximum degree of G. Okay, very good. Now you can actually directly from here you can actually see that this implies that, because you can take mod inside here, no issue. So mod lambda 1 is always less or equal to the maximum degree of G. In fact, you can always see this. Okay, very good, very simple proof. We have already seen this proof earlier, but now we have done it for signed case. Okay, what next? Now maybe you have immediately realized that we can make use of this beautiful fact using the eigenvalues of an, because an is again signed adjacency matrix. Okay, and then we know the eigenvalues of an, and by using Cauchy interlace we can directly come to the conclusion. Okay, so now let us see the I mean maybe this you can write it as a corollary, or maybe just a proof of the sensitivity conjecture. So proof of the conjecture of the sensitivity conjecture. Okay, now what is lying at? Very simple thing. Okay, what you do, okay, you pick a subgraph. Okay, so let H be the subgraph of induced subgraph of Qn, okay, with number of vertices, with the number of vertices in H is equal to 2 raised to power n minus 1 plus 1. Okay, now what will be let us see what will be its eigenvalue. So one thing is for sure, so let me call so let us take what you do. You take any signed adjacency matrix of this, any signed adjacency matrix of H, right? And we know that this has to follow this quantity, right? I mean the maximum degree will be greater or equal to the largest eigenvalue of this matrix, the signed adjacency matrix. Okay, but we can actually very nicely take out some nice signed adjacency matrix. This we can trim out from an. Right, this we can trim out from an. Okay, because an is nothing but the signed adjacency matrix. An is signed adjacency matrix of Qn. We have just seen. Okay, now here take rows and columns corresponding to H. Take rows and columns corresponding to vertices in N, vertices in H. Okay, by the way we already know what will be the largest eigenvalue. So suppose this is now adjacency matrix of AH. Okay, the signed version of this, right? So signed version. Okay, signed version of this. We have already seen that this will be always less or equal to delta H. This will be always less or equal to delta H. Now what next? The lambda 1 of AH by Cauchy interlace theorem is always greater or equal to lambda 1 plus the difference of the size of these matrices. So what is the size of matrix an? It is 2 raised to power n. Okay, and what is size of this matrix AH? It is 2 raised to power n minus 1 plus 1, right? So this is plus 1. Okay, and of which matrix? This of AS you can write. Yes, the signed adjacency matrix of the bigger graph of Q, right? Okay, very good. So now this gives what? So this means what? This is nothing but 1. This is lambda 1 not. This is in fact, wow, powerfully 2 raised to power n minus 1 of AS. Okay, so maybe write this of AS. So what is this eigenvalue? 2 raised to power in the sequence 2 raised to power n minus 1. What is that? we have already seen that the eigenvalues of this matrix are nothing but square root of n minus or square root n with equal multiplicity are 2 raised to n minus 1. Hence the eigenvalue here will be, the value will be here square root of n. Okay, so this is nothing but square root of n. So that means from here you can actually write that this quantity. So lambda 1 of ah, okay, is less or equal to this, which is in fact following this, right? So square root of n, and we are done with the proof. So that means what? So the maximum degree of h is at least, so maximum degree of h is at least square root of n. Okay, so this is a very elegant proof of sensitivity conjecture. I hope you enjoyed it. Okay, so rather than adjacency matrix, we have made use of signed adjacency matrix. Okay, and because the eigenvalues of the signed adjacency matrix was coming out to be square root of n and minus square root of n, which was not the case with our adjacency matrix, the usual adjacency matrix. Okay, on what cases or on what conditions this inequalities will be very tight, okay, and what will be more implications of this result, we will see all this in our tutorial and assignment. Okay, till then, thank you very much. Okay.